So 10.1.3, definition of an exponential function. In example 4, we're asked to evaluate the expression 3 times 2 to the t for t equals 0, 1, 2, 3, and 4. Okay, so evaluate is another one of our verbs that we've seen a lot this semester, and that just basically tells us to do the math, follow order of operations, until we get a single number for an answer. So the expression they give us is 3 times 2 to the t, and just like before, we're going to put parentheses around our variable before we substitute. So we're going to get 3 times 2, and for t we're going to substitute a 0. Okay, from the previous page of notes, we know that 2 to the 0 power is 1, so this gives us 3 times 1, which is 3. Okay, exponents happen before the multiplication, so following order of operations, we did the math until we got to a single number. Now if we take this same expression and we're going to substitute 1, and then we're going to substitute 2, and then we're going to substitute 3, and finally we're going to substitute 4 for t. So 2 to the first power is 2. Again, exponents happen before the multiplication, and 3 times 2 gives us 6. 2 squared is 2 times 2, is 4, so 3 times 4 we get 12. 2 cubed means we have 3 factors of 2 all being multiplied together, so 2 times 2 times 2, which is 8, and 3 times 8 is 24. And finally 2 to the 4th, so 4 factors of 2 all multiplied together, so we have 2 times 2 times 2 times 2, which is 16, and 3 times 16 is 48. So below is the data from the first page of these lecture notes. And we're asked what we notice about the outputs below. So that would be these. Okay, so we've got an input-output table, so these are our inputs, and these are our outputs. And the answers you got in example 4, which are up here. So the answers we got here were 3, 6, 12, 24, 48. The outputs we got here were 3, 6, 12, 24, and 48. So we should notice that they are the same. Okay, or that they match. So the relation between time elapsed and number of bacteria, so time elapsed, okay, that was our input, and number of bacteria, this was our output, there's our 2 variables, can be described with the following function. So the number of bacteria at time t is 3 times 2 to the t. Okay, that was the formula that worked for each of these inputs, gave us exactly the output that we had in the table. So this leads us to a new family of functions for this particular unit. So an exponential function. An exponential function is a function whose equation can be put in the form f of x equals a times b to the x. And so actually if we want to write this, these are mushed together, but this is really an a times b to the x. Okay, a cannot be 0, and this base number, we're going to see as we're looking in the table what we keep multiplying by is some positive number, and that base cannot be 1. Okay, so if we look at the table of data above, and the function n of t equals 3 times 2 to the t, describe how these constants a and b are related to the patterns in the table of data. Okay, so if we go back up to this table, we noticed on the first page that as we kept increasing our inputs by 1, our outputs over here kept being multiplied by 2. And we can see that here too. 2 to the 0 was 1, 2 to the first power was 2, it's doubled, and our answer doubled. And then here we had 2 squared, okay, so again it doubled again, and then 2 cubed, it doubled again, and so on. So this base, this number here too, seems to be what we multiplied by. So these were what outputs multiplied by when x increased by 1. But now what about this 3? So here, this is our initial number of bacteria at time t equals 0. So just like with linear functions, okay, we looked at kind of an initial value and then how much it increased or decreased by. The same thing here. So we have this initial value when t equals 0. And then again, this base here gave us what was multiplied, what we kept multiplying those outputs by as x increased by 1. So let's compare linear functions to exponential ones. How they look pattern-wise different, and then how that's expressed differently in their equations. So in this particular set of data, our input variable x kept increasing by 1, and we can see that our outputs here keep going up by 2. Constant change in input leading to constant changes in output tells us that we have linearly related data. Okay, which means that we have, this f of x equals, some constant. So when we looked at the calculator, or we'll use the notation from algebra, like b plus mx. Okay. Or mx plus b, but in class I've been writing it this way to emphasize our initial quantity and then how much it went up or down. So in this case, our initial starting point was 3, and then we kept going up by 2 for every unit increase in x. Okay, so here we've got addition, because our outputs we kept adding on 2. And here, this is multiplication, but we use that multiplication to represent the repeated addition. Now I want to add 2 and add 2 and add another 2. So to get from 3 to 9, I really want to add on 3 2's. And well, we can do that with multiplication. Instead of add 2, add 2, add 2, we can add 2 times 3. But now this new pattern, as we keep increasing x by 1, over here instead of adding or subtracting like we did with linear functions, okay, over here, we are multiplying by 2 each time. Okay. This is going to be what we're looking for to say that we have exponentially related data, meaning that we can describe this relation with an exponential function. Okay. All right, so we have this kind of initial starting quantity and then our base multiplier that we're using. So in this case, it started at 3, and it kept doubling. So here we can see that we have multiplication. To get from one output to the next, we kept multiplying by 2. And then here we have an exponential piece, 2 to a power, but again, that's our shorthand notation in mathematics for repeated multiplication. So again, we should recognize the difference in the patterns between linear and exponential, and then again, how that's going to be represented differently in how we describe that relationship with the function notation. So 10.1.4, models whose equations involve negative integer exponents. So the force F in pounds that you must exert on a wrench handle of length L in inches to loosen a bolt is described by the equation F of L equals 720 over L to the negative 720 times L to the negative 1. Okay, so again, the input here, so the way this is written implies that we have ordered pairs that look like this. Okay, the input is length in inches, and the output is force, and that's measured in pounds. So part A says to simplify the right-hand side of the equation. Okay, so simplify, we said, again, that's another common verb we need to know, and the definition of this one kind of keeps expanding depending on what types of expressions and equations that we've looked at. So if we simplify, for right now, this means 3 things for us. It means to remove grouping symbols legally with correct mathematics, combine like terms, And for a long time in this course, that's all it meant to us. But now we have these expressions that could have negative exponents. So to simplify means that there can be no negative exponents in our expression when we're done as well. Okay, so if we're looking at the right-hand side of the equation, this expression, 720 times L to the negative 1, there are no grouping symbols. This is all one term, so there's no like terms to combine, but it does have a negative exponent attached to the L. Okay, so earlier in this particular section, we learned that when we see a negative exponent, we should think of reciprocal. So this is 720 times, and then that L to the negative 1 we can write as 1 over L to the positive 1. So this gives us f of L equals 720 divided by L. Okay, so if we rewrite this equation where the right-hand side has been simplified, it looks like this. So now we're asked to compute f of 12. So again, before we substitute for a variable, we're going to put parentheses around that variable. So this means we're going to get 720 divided by 12. And so 720 divided by 12, we get 60. So if we compute f of 12, we get 60. And if we actually put some labels back on these units, or on these numbers, and interpret in context, again, this means as an ordered pair, the input was 12 inches, and the output was 60 pounds. So if we put the context back into this problem, it tells us that if we have a wrench handle that's of length 12 inches, it will take a force of 60 pounds to loosen a bolt. Okay, so if our wrench has a 12-inch handle, it will take 60 pounds of force to loosen a bolt with it. Alright, so the last topic in this section requires or involves using scientific notation. So many times when computing values in mathematics and other fields, you end up with extremely large numbers or extremely small numbers. So for example, okay, the Earth is, we've got this huge number here, kilometers from the sun. Okay, 149,600,000 kilometers from the sun. Or we have something that's really teeny, teeny, tiny, almost zero. So a muon lives for about 0.0000022 seconds before it decays into something else. Or there are about some monstrous number here, different samples of size 20 from a population of 300 people. Okay, that's pretty amazing to even think about as we're taking samples from a group of 300 size, all the different possible samples of size 20. Okay, there's like bazillions of them. Okay, and there is about bunch of zeros, 9.3 chance of randomly picking 30 students from Harper's database and getting all females in that particular sample. So again, it could happen, but really, really unlikely as we start looking next semester at probabilities. So there must be some other way to write these numbers without writing all of those zeros. And the notation that we use is called scientific notation. And we're going to find next semester that many times when we start computing probabilities, when they are really small, even if we don't want it to, the calculator is going to naturally put those answers in scientific notation. And we need to know what that notation means. Okay? So a number is said to be written in scientific notation if it's of the following form. So some number times 10 to a power. Okay, where k is any integer. Okay, so remember what an integer is. Okay, this can be negative whole numbers, 0, and through our natural counting numbers. So integers, we have positive and negative whole numbers. Okay, so k can be any one of these integer powers. And n, the number that we wrote to begin with, it's basically, we've got one number before the decimal that's not 0. Okay, so in the negatives, it's between -1 but not quite 10, or in the positives between 1 and not quite 10. Okay, so this basically says that the first number can be positive or negative and must be a single non-zero digit. So let's rewrite the following without